Lesson. So in this lesson, we're going to be covering the first technique of the numerical integration series, and that's going to be the trapezoidal rule. The series is going to be made of 3 techniques to find the area under the curve, which is the main purpose of the concept of integration. Now, in calculus, you've done this using what are called integration rules. You've done this using the power law, you've done this using integration by parts, partial fractions. Now in this lesson, we're going to be covering how to find the area under the curve without resorting to integration rules. Because sometimes you'll be dealing with functions that are too complex to deal with integration rules, and also sometimes the integration rules are not sufficient to find the integral of the function or the area under the curve for a particular interval. So let's actually recap what it would look like using the integration rules. So if you look at the top left here, the analytical solution, we're going to be dealing with the function ln of x, and we're going to be finding the area from 2 to 4. And for this particular function, the integration rule that you would use is integration by parts. And when you apply this, you're going to be getting x ln of x minus x. And when you evaluate it between 2 and 4, you'll get an area of 2.15888. And this is going to be our barometer later in later lessons of the accuracy of the numerical integration rules. So how does the trapezoidal rule work? Well, the trapezoidal rule uses the simplest function, which is a polynomial, and uses one of the simplest functions within the polynomial, which is a first order polynomial or a linear function. So for a particular interval, for this example is between 2 and 4, instead of defining the function in terms of ln of x as this blue line, I'm going to define it as a linear function. And you can see that this is the line that I have, the blue line here. This is the linear function that I'm defining this interval 2 to 4. And what I'm going to do is I'm going to find the area under this first order polynomial. And if you notice, the area under a first order polynomial has a geometric shape of a trapezoid. And this is where the rule gets its name, the trapezoidal rule. So what is the area of a trapezoid? Where the area of a trapezoid is the width, which in this case is b minus a, multiplied by the average height, which is the function of a, f of a, plus f of b divided by 2. And that will get us the estimate of the area under the curve for ln of x between 2 and 4. And if you look here, it's actually a pretty decent approximation, right? You have encompassed most of the area under the curve. And if you look at the white space between the yellow line and the blue line, this would signify the error that we have. So this is the only error that we have for this particular problem. Now, what if we want a better approximation? What if we want to eliminate some of this error? Well, you have one of 2 ways to do it. One, you can use a higher order polynomial than a first order, and that's going to be covered in the next lesson. Or we can use more trapezoids under this area to define this area. So let's actually see what it would look like if we would use 2 trapezoids. So if you look here, we have 2 trapezoids, the green trapezoid and the yellow trapezoid. And in this case, they are going to be evenly spaced. Here, the width instead of 2 here is going to be the width for each is going to be 1. And to estimate the area between 2 and 4 for ln of x, what we're going to be doing, we're going to be combining the area of the 2 trapezoids. So the area of the first trapezoid is going to be h multiplied by the average height of the first one, which is going to be f of x naught plus f of x1 divided by 2, plus the area of the second one, which is going to be the width h multiplied by f of x1 plus f of x2 divided by 2. Now, let's actually perform a little bit of an algebraic manipulation here. Let's take h divided by 2 as a common factor. And also you're going to find that f of x1 here and f of x1 here, so it reduces here to 2f of x1. Now I want you to keep an eye on this 2f of x1 term, because the popping of this term is going to be the basis of this generalized equation that is going to be the basis of this entire method. So how about if we want even a better approximation? Well, we can add another trapezoid. So you can see here we have 3 trapezoids. We have the green, red, and yellow trapezoid. So we're going to be making them evenly spaced with a width of h. And again, much like with the 2 and much like with the 1, to find the area for ln of x between 2 and 4, we're just going to combine the areas of all three. So the area of the first one is going to be h multiplied by f of x naught plus f of x1 divided by 2, plus the second one, again, they're evenly spaced, so the width is still the same, h multiplied by f of x1 plus f of x2 divided by 2, plus h multiplied by f of x2 plus f of x3 divided by 2. Now, much like with the two trapezoids, let's take h divided by 2 as a common factor. And also we have f of x1 here, f of x1 here, so we have 2f of x1, and we have f of x2 here, f of x2 here. Now we have 2f of x2, and you can see that another term here popped. And this is a pattern that we're going to be using to create this generalized function. And you can see that when I added one more trapezoid, the term 2f of x2 popped up in the equation. And this is a pattern that's going to happen every time I add another trapezoid. So if I add a fourth trapezoid, you're going to find 2f of x3 pops up. And if I add another one, 2f of x4 pops up, and so on. So let's actually see how does this work in terms of this generalized equation. So this equation is made up of h, which is the widths of each of the trapezoids. F of x naught, this is going to be our function at the lower limit. F of xn, this is the function at the upper limit. And this term here is going to take care of the middle terms that we have here. So let's actually test this equation and see, will it in fact reduce to these three equations that we formed here. So let's assume we have two trapezoids. So if we have two trapezoids, n is equal to 2. So here we have 2 minus 1, so that's going to be 1, which means we have only one term here, which means this is going to be 2 f of x1. And since n is 2, this is going to be x2 here. And you're going to find that this formula, in fact, reduces to the one we have for two trapezoids. So let's actually test it also for three trapezoids. So three trapezoids, n is equal to 3. So we have 3 minus 1, so we have 2, which means we have two terms within this sum. So it's going to be from I equal 1 to 2. So it's going to be 2 f of x1 plus 2 f of x2. And you're going to find that we generated the two middle terms here. And of course, because n is 3, this last term here becomes f of x3. So this did in fact reduce to this last one. So let's actually see if this actually works also for one trapezoid. So one trapezoid, n is equal to 1. So if you see here, when n is equal to 1, 1 minus 1, this is 0, which means this entire term disappears. H is just the upper limit minus the lower limit. So h here is just b minus a, and here divided by 2. And f of x naught is just the function at the lower limit, which corresponds to f of a here. And f of x, in this case 1, which is the same as f of xb. So this in fact did reduce to also using one trapezoid. So the entire trapezoidal rule is encompassed in this equation, which is a function of h, which is basically knowing the upper limit and the lower limit, and also having the function that you are interested in getting the area under, which in this case is ln of x. So if you know your integration limits and you know the function, you can basically get the area under the curve of this function using this very simple technique that is based on the equation of the area of a trapezoid. So it's a very simple technique. So to recap what we actually learned in this lesson, we learned the first method of numerical integration, which is the trapezoidal rule, and we found that it's based on a very simple technique of defining the interval that we're interested in terms of a first order polynomial, and we found out that the area under a first order polynomial is in fact an area of a trapezoid, and the area of a trapezoid is defined as the width multiplied by the average height. And we also discussed that if we want a more accurate approximation, one way to do it is to use a higher order polynomial, which again we will discuss in future lessons, or we can use multiple trapezoids under this area. We examined two trapezoids and also we examined three trapezoids, and by noticing a pattern in the middle terms, we created this generalized equation that can be used to estimate any area for any function that you are interested in. So that will be it for this lesson, and I will see you in the next lesson.